All right. So Ankit, thank you for joining the Boston Computation Club, which is a small but powerful quorum today. And we appreciate your time. Ankit and I have collaborated for a while now on a project that is in the works. And so I've gotten to see a lot of his really exciting ACL2S stuff in practice, but I'm not as familiar with it in theory. And so I'm quite excited to see this talk today and learn about some of the foundational theory behind some of the cool things that Ankit can do with ACL2 Sedan. So Ankit, with that, the floor is yours. Please take it away.
Thanks, Max. Hello and welcome to my talk on Mathematical Programming Modulo Strings. I'm Ankit Kumar, a PhD student at Northeastern University, and this is joint work with Pete, who's my advisor. So string solving has generated a great deal of interest in recent times due to its application in fields like security, software engineering, verification, and programming languages. So a theory of sequences deals with constants, sequences consisting of constants and variables, which are formed by concatenation, and equalities between those sequences. The theory of strings is just the theory of sequences in which constants are characters. So following is an example of a string equation where x and y are variables, a and b are constants, and we need to find a solution such that if we replace x and y with some sequences of characters, then an equality holds. So why don't you try and okay, I think somebody else has joined. So I was just giving an introduction to string equations. So on the screen, you can see that we have a equality between two sequences. The variables are x and y, which can range over a sequence of characters. And the job is to find a substitution for those variables x and y such that the left and the right hand sides match.
So it seems to me one letter solutions don't really work, at least, and two letters are harder.
Yeah, so Artem has a good point that even no letters can also be substituted. For example, x could be empty, but let's see. Let's assume that x is empty. And if we substitute for x, we get aby equal to by. And clearly, both of them start with different letters. So this is unsatisfiable if we assume x is empty. However, both sides, on the right-hand side, we see that it starts with a b. So how about x should be something that is b or starts with a b. So if we replace x by b, we get this. Now, maybe an equality holds for some value of y. So if we get rid of the leading b's, we get this simplified equation. So now we see that we have to find a substitution for y. How about we replace y by the empty string? If we do that, then this is unsatisfiable. So since the left-hand side starts with an a, so let's replace y with an a. And this also doesn't work. But as Artem suggested, we could have sequences that are longer than one character. So since the left-hand side starts with an AB, we could try y as AB. And but that also does not work. And we could keep going on and try to discover more substitutions. But that is hard work. So we need a better way to be able to find out inferences and proceed accordingly. So why don't we put them side by side and observe that the lengths of xby and byx will have to be the same for any solution of this equation, right? So we can decompose this equation, and this gives us two equations, which is equisatisfiable to the one that we started with. So if this is satisfiable, then the initial solution, then the initial equation was also satisfiable.
I'm sorry, how exactly did you decide where to split
Yeah, so we split based on the decision that the lengths of xby and byx will have to be equal for any substitution of x and y.
In other words, xby is a permutation of byx, but xa isn't a permutation of by. So you went from the right leftward and looked for the split where you would get a permutation, and therefore they'd have to be the same length.
Cool. That
yeah,
makes sense.
Or more simply, you can think of the length of xby is length of x plus length of y plus b. And length of the right-hand side is length of b plus length of y plus length of x. And since plus is associative and commutative, so equality holds. And from that, we deduce that these must be equal. So we applied decompose and observe that in the first equation, xa equal to by. So we can get rid of by here and replace it with xa, because the conjunction of these two equations has to be satisfiable. So we rewrite, and now we have x appearing on both the sides in the start, and we can get rid of that. And then we end up with this, which is unsatisfiable because they both start with different letters. So now, because this is unsatisfiable, the initial equation we started with is also unsatisfiable, and there is no way we can find a solution. So these are some of the techniques that we utilized in our tool. Let's look at this equation. This is pretty big, has 6 variables and 3 constants. And I will not ask you to solve this because it will take a lot of time. So let's ask existing string solvers. And for string solvers, because there are just 6 variables, it should be easy, right? So it turns out that's not the case. So this equation was unsolved by CVC4, NORN, G3STR2, and G3STR3 even after 1,000 seconds, which is a lot of time. Even in SMT competitions, a lot less time is given for solving problems. However, our implementation of the tool was able to get it within a second and came up with the following solution. So
was this a motivating example for your tool, or is it just sort of emergent in the wild? This is an example where your tool does better.
So the point of this slide was to show that if you compare this performance to modern SAT solvers, which can solve problems consisting of thousands of variables in a matter of seconds, we see that modern string solvers have not matured enough. And there's plenty of room for improvement. The fact that what we started with was a very coarse analysis of our method, and there was not a fine tuning that went into it. There is a lot to be improved in this field.
Gotcha.
So let's look at the problem and its history. So in 1946, Quine first...
Yeah. The approach that you showed with splitting the equation, was it what your tool does, or is it something that string solvers generally do?
Some tool. So this is some of the techniques are also shared by other tools as well, like looking for lengths and decomposing based on lengths. Some other tools do that, like Z3STR2 also does that. But we'll come to the novelty in a few slides.
Okay, cool. Thanks.
So the problem is has been studied for a long time. In 1946, Quine first proved that the first order theory of string equations is equivalent to that of first order arithmetic and hence is undecidable. And then in early 1970s, there were some semi-decision procedures that could solve if there was a solution, but not, but it could go into an infinite loop if there was no solution. In 1977, McCann first solved the general problem of string equations and proved that it is decidable, and also gave an algorithm to solve it. And after that, there were a series of results on trying to establish the bounds on the complexity. It started with 4 NEXP time and was gradually reduced to T space. And recently in 2013, just gave a very simple decompression-based proof for proving the complexity of string equations to be in p-space. And it is conjectured right now that it is in NP, but maybe we'll see it later. Our motivation for having a decision procedure for string equations came from the array processing language Remora. So every term in the language Remora, Remora is a high-level dependently typed array processing language. So every term in Remora is an array. During compilation, the shape of each terms need to be inferred. For example, A is an array whose length is unknown, let's say X, and whose width is known to be 4. Let B be an array whose length is 3 and whose width is unknown, but we do know that its width is equal to the length of A, which is assumed to be X. And then to successfully apply the plus operation, we require that the sequence X4 is equal to 3X. And this sequence turns out to be unsatisfiable. And if that is the case, then the type inference algorithm of Remora would deem that the term plus AB is ill-typed. So we saw some of the rules that are used in solving string equations. We also use some other rules like var substitution and var split, but these are very complex and I'm not going to discuss these here. Instead, I'll show their application in how to solve string equations. So now we are going to look at some more rules and get a feel of what exactly goes on when solving string equations. So first of them is EQ length. So consider the string equation xa equal to x. This is unsatisfiable because if you compare the lengths of the left and the right hand side, this is an unsatisfiable linear constraint. So if you ask an LIS solver about this equation, it will return unsat. Similarly, EQ consts counts the number of a particular character appearing on both sides. So in AX equal to XB, which is equivalent to the problem we just saw in Remora, if you count the number of A's appearing on both the sides, it is equal to 1 plus the number of A's in X equated to the number of A's appearing in X. So this is unsatisfiable. Now, another is var elimination. So if you have a conjunction of two string equations and one of them has a variable on one of its sides, we can immediately get rid of that variable by substituting for that variable its corresponding other side into all the other equations. So we get rid of x and put cy in xa equal to ax to get this, which is unsat because both of them start with different letters.
Quick question about the previous. I'm curious here, x, does it stand for the variable in your equations, or does it stand for a meta variable that says any string that can consist of variables and terminals or characters, if that makes sense? Because like xa equals x, you don't have to have literally this, right? You can have any string ended with a equals to that any string, shouldn't be satisfiable, right? So my question is just a formulation sort of question. It's not like
So as I described earlier, variables can range over sequences. So x can be another variable, let's say y, but then we would generate another constraint that nxa equal to nya. And so the more variables we introduce, the more constraints we generate and push them back to the LIS solver.
Yeah, I guess what I was trying to say is that in principle, that can stand for an infinite amount of equations. So I'm just curious how you handle this. So xa equals x may stand for, again, a lot of equations, right? For particular choices of x.
I did not quite get that.
Like so I guess you're not trying to generate or do you, or I guess you will show it, right? Whether you're trying to generate like specific instances of this xa equals x. And so
we are trying to find one solution of
Mhm.
X, or I mean, one ground substitution that consists of just characters such that the left and the right hand sides are equal.
Okay, yeah, thanks.
So another rule is variable splitting. So if you consider the equation xxa equal to cyx, note that x starts with a c. So we could replace x with cv for some other variable v. And then we have the following equation. And if we trim the c's from the start of both sides, we get this equation. And this can be decomposed. Note that VA and CV have the same length. So we get two equations, VC equal to V and VA equal to CV, both of which are unsatisfiable. We can also utilize variable substitution. So notice that whenever two or more variables always appear together in your problem, like W, U, and Z, this can be substituted by a single variable. So this simplifies to just replacing W and Z by X. And we have already seen that this is unsatisfiable in the previous example. EQ words is just like EQ length and EQ characters. So we count the number of words occurring on both sides of an equation. So in this case, if you count the number of times the word CA appears, so we count the number of times CA occurs in X plus 1 plus the number of times CA occurs in Y. Note that there cannot be any count of CA from X to B because CA ends in an A, so there will be no transitioning words. And also there can't be any transitioning words from A to Y. So we have 1 plus number of CAs in X and number of CAs in Y. And if you look on the right hand side, it's just the number of CAs in X and the number of CAs in Y. Again, there can't be any transitions from the last letter in Y to C and from A to the first letter in X, because the first letter has to be C. So this is unsatisfiable as well. So we have a lot of these rules, and but the thing is they have to be orchestrated in a way, in a clever way, such that inferences are driven fast and we don't have to do a lot of exploration. So we have a transition system for that, TranSeq, that accepts a conjunction of sequence equations Q init and linear constraints C init as input. The linear constraints can be constraints on the lengths of variables occurring in the string equation. Like you could say that for this equation, give me all solutions that have the length of X equal to 5. So that is a linear constraint, which you can provide as input. Using this input, TranSeq generates an initial configuration K init. This is done by some pre-processing steps like getting rid of equalities and compression of sequences to have if A is appearing 5 times consecutively, you can compress it into a block and say that it's a tuple of A, 5, where so the block is a much simpler representation of a sequence. After creating an initial configuration, TranSeq applies enabled rules to configurations non-deterministically. By enabled, we mean that they have to a configuration has to satisfy some properties enabled in order to be applied to a certain rule.
Ankit, could you say again, what is a configuration?
The configuration is kind of like a state for our transition system. So we can say that in the process of solving this equation, we are in this state. It denotes that we have explored this much and this much is left to be explored. We will shortly be looking at the configuration as to what it is.
All right.
But for now, assume it's a state. So generated linear constraints are incrementally pushed to a background linear solver. We have already seen examples of linear constraints that we generate, like EQ length, EQ constants and EQ words. The LIS solver is queried for satisfiability and decomposition. So while exploring our path, that is where mathematical programming comes in, and theoretically and practically complete for general theory of string equations. So TranSeq is based on the MPMT framework that is used to combine decision procedures like, like SMT. But in SMT, we require a SAT solver in the backend that orchestrates different rules. Here we are utilizing an LIS solver. So that is our novelty. And we found that it works pretty good, as we will see later. It is highly non-deterministic system that allows branching and pruning of states while searching for a solution. And it communicates with the background theory solver using interface variables. So the theory here is the theory of strings, and that communicates with the background LIS solver using some interface variables that are common in both the theories.
Just to make sure I understand the novelty, LIA is some kind of stock software that you take and plug it into MPMT, right?
Yes. Okay. So what we used is the Z3 LIS solver, and it's a decision procedure for arithmetic. So we can for linear integer arithmetic. So we assume its soundness and completeness, and we use it as a backend to our tool.
Cool.
So this is a configuration, and this slide shows a visual depiction of the process of finding a solution. The root node is the initial configuration KINet, in which we have Q, which is a set of compressed sequence equations, which we derived from the input sequence equations. Sigma is the set of substitutions, which is currently empty because we haven't done anything yet. Vars is a superset of all the variables occurring in sigma and in Q. And C is the set of linear constraints. So this is our configuration, and we keep changing it according to where we move in the process in our derivation tree. So let's say we apply Diffvar's rule, where Diffvar says that either X is a prefix of Y or Y is a prefix of X. So you could have branching. If you branch, you go to another configuration, you generate certain new variables that are added to ours and do substitutions such that Q also gets updated. So in this way, we keep applying rules until we reach either an unsat node or a sat node. If you reach a state where all of the leaf nodes are unsat, then we know that there is no solution. So once the sat node is reached, substitutions of input variables in the sat node may be in the form of new variables that we introduced while coming here. So in order to obtain a concrete solution for input variables, we need to get concrete substitutions for the new variables that were introduced. And in order to do that, we need to find substitution for variables introduced at each step until we reach the root node. This takes us back to the sat node all the way up, from the sat node all the way up to the root. So now we are going to discuss correctness properties of TranSeq. TranSeq is sound, which means it never lies. So if it returns sat, then the initial input consisting of string equations and linear constraints was indeed satisfiable, and it will return a satisfying assignment. If it returns unsat, then the input conjunction of string equations and linear constraints was unsatisfiable to start with. It is partially correct, which means that it is sound and terminating, but it may return unknown. The termination result here depends on the bounds of lengths of minimal solution of string equations. So you can think of exploring the tree until the LIS solver says that now we have lengths of equations exceeding this limit, and there we need to close off the tree, and that becomes unsat. And it is fully correct in the absence of input linear constraints. So it is partially correct. And if you don't provide any input linear constraints, it will never return unknown. This happens because you could say that give me solutions in which X has length greater than 5. But let's say the solution was solvable only for lengths of X less than 5. In that case, there may exist solution, but it is not able to find it. And therefore it returns unknown. So, however, the theory of string equations with linear constraints is open right now. We don't know whether it is decidable or not. Our tool SeqSolve was implemented, is an implementation of our transition system TranSeq. We implemented SeqSolve in ACL2S, which allowed us to easily define complex data types. For example, in order to represent a sequence, you need characters, you need variables, you need length expressions, because when you compress, the length of a block can also be an expression, a length expression consisting of variables and operations. Sorry. So a block is a pair consisting of a character and a length expression. An element in a sequence is either a character, a variable, a unit variable. So unit variable is another kind of a variable that has a fixed length of 1, or it can be a block. A sequence is a list of elements. A substitution sigma is a dictionary of variables to sequences. An equation is a pair of two sequences, and the set Q is a set of equations, and a set is represented as a list in ACL2S. So we have this, and once we have these def data structures, we can apply check equal to check whether a given sequence is actually a sequence. So we ask using the predicate seqp that whether this is a sequence, and it returns true. So in ACL2S, we can also define rules on complex data types. So our var elimination rule is defined such that it accepts a set of equations. It has an accumulator for equations because it is tail recursive. It has a substitution sigma, and it returns a pair of substitutions and string equations. So if this is admitted, then it means that this function is terminating, and it respects the types. We also used ACL2S to define the Z3 expression grammar such that the constraints we generate and send to the backend LIS solver are actually terms in the type Z3 LEXP. So notice that these are just terms consisting of operators, comparison operators, followed by two length expressions in the prefix notation. And this is the way Z3 accepts inputs. So in this way, we are sure that we are not sending garbage to our background solver. We can also define functions on complex data types. So if we need to find the length of a sequence, we provide a sequence and we expect a length expression in return. We define equate length as equating lengths of two sequences, and this we return as a Z3 length expression, which is then added to our which is then sent to the LIS solver incrementally. Finally, we also have a Z3 SQL2S interfacing library developed by Andrew Walter, and we can add assertions using that library to talk with our LIS solver, and we can push and the way we do incremental solving is by doing a push, add assertion, check set, and pop. So this assertion was valid only till solver pop, and after that the LIS solver will not have this assertion in it. So in this way we explore by adding more and more constraints. We evaluated our tool on benchmark problems. So that included all publicly available benchmarks we could find, restricted to the general theory of string equations and length constraints, right? So it includes problems from Kaluza, string-first, and also some handcrafted benchmark problems that were relevant to Remora, or the problem the kind of problems that Remora inference engine would have to face. We compared our solver against all string solvers we know that we can that can solve problems in our theory of interest, which includes string solving with linear constraints. So the solvers we compared against are CVC4, NORD, Z3STR2, Z3STR3, Sloth, and Trow. So here's a result of our evaluations. In the solved column, the number of problems solved is broken down into problems solved in each of string fuzz, Kaluza, and handcrafted benchmark problems. So if we total it, the total number of problems were 1,178. SeqSolve was able to solve all of them in 176 seconds, and it had 0 unknowns, 0 timeouts, and none of them were incorrect results. CVC4 took some less time, but it timed out on 50 of the problems. It took 3,200 seconds, including the timeouts. Z3STR3 was able to solve 947 problems, and it timed out on 225. And similarly, Z3STR2 took the least amount of time, but notice that it returned unknown on most of the problems, more than 60% of the problems. Trow and Sloth gave incorrect results on 1 and 64 problems. We will present our results of the evaluation in terms of a ray plot.
Sorry, quick question about the previous. What are those numbers with slashes in the solved column, like 780, 344, 54?
Yeah, these are the breakdown in each of the benchmark problems: Kaluza, string fuzz, and handcrafted.
I see, thanks.
So we now present the notion of ray plots. This is the simplest way to compare solvers, as we found out. The y-axis represents expected time in seconds, and the x-axis represents expected number of problems solved. For example, let's consider the 600 problem line. And if we ask the question that how many solvers can be expected to solve 600 problems? So Z3STR2 cannot, because it returned unknown on most of the problems, and it did not reach 600. SeqSolve was the fastest to solve 600 problems, followed by CVC4, followed by Trow, and similarly. So if you look at the x-axis, you get an idea of which are the fastest to get up to that many problems. So we can expect a solver to solve 600 problems in this much time by looking at the y-axis. Now, if you fix the y-axis, let's say the 8,000 second line, then in the given benchmark, SeqSolve solved all the problems in 8,000 seconds because it lies here. Z3STR3 and NORD were able to solve about 550 problems. Sloth about 850, which is here. And CVC4 solved 1,100 problems, which is less than 8,000. So this is very different from a cactus plot, because when using ray plots, less is more. In a cactus plot, problems are ordered on a per tool basis from the easiest to the hardest. This ordering can vary significantly from one tool to the another, and a user of a tool may have no way of knowing how easy or hard a particular problem is going to be. So we remove that from the graph and present a simplified view, so that if you want to select a string solver for your application, you can just estimate based on the number of problems you have, which is the fastest, and you can just select a tool. So in conclusion, we presented a new non-deterministic branching transition system, TranSeq, for deciding the satisfiability of conjunctions of string equations and length constraints. Evaluation showed that SeqSolve solved more problems and was faster than existing solvers. In the future, we plan to reason about the implementation using the ACLTO's theorem prover, and we also plan to add support for a richer class of constraints. Thank you.
Ankit, thank you very much. Also very cool QR code. I've never seen that before in a academic talk. Looks like Artem has a question. Artem, why don't you take it away?
Sure.
Yeah, Julia first, and then I.
So I was wondering, when you were describing the transition system, does it matter which, like, have you tried different order of applying different rules? You've showed a bunch of rules for checking SAT and SAT. Like, does it matter? Does the order matter? And if yes, how?
This is just an example of one evaluation, and it is highly non-deterministic. So the labeling of rules are completely examples. It could happen that starting from the init, you just know from li unsat that it is unsat, and you end right there, like we saw for x equal to x.
So does it take any of the rules that are applicable at this point?
Yeah. So for example, diff vars is applicable when on both the sides you have sequences starting with variables.
Mm-hmm.
If one of the sites does not have a variable, it has a character or a block, you will apply var const. So that is what is meant by enabled rules.
Okay, gotcha. Thank you.
And the follow-up to this, you said the LIA solver can know that it's unsat from the very beginning. Does it mean that you, for every state, you try to call the LIA just in case, sort of?
No, we don't need to call LI unsat for every state. It can be called after a few states as well. Like, however, in our implementation, we do it every time, because from profiling, we came to know that it's much faster to apply to query the LIA solver at every step rather than delaying it.
Yeah, that was my guess too. Okay, that's good to know. And my question was more general one. So the results look really impressive, at least for me as an outsider. You said that you were motivated by this problem in Remora. Were you able to apply this system to it, and like, what was the result, or is it a future work?
Yeah. So so this was the motivation. And Justin was working on Remora. However, he wrote his own implementation in order to complete his PhD, and that was based on the Mackinnon's algorithm. It had a few problems. Like, on some of the problems that we have in our benchmark, it would go in I can't say infinite loop, but a long loop. I mean, it would take a lot of time. But for the kind of problems that Remora gives, it's generally restricted to one or two variables, and it's usually they're not overlapping. So they're pretty easy problems. Yeah.
It was. I understand it was the state before you sort of started. There is this application, but like, are you going to, like, right now, after you've sort of finished this part of work and you seem to have the working system, are you going to apply it, like, to fit it into the Remora, I don't know, type checker or whatever, or
inference? I mean, it seems like kind of an application work. Like, if somebody's working on extending Remora, it would make sense for them. But in the near future, I don't see myself working on Remora.
Okay, makes sense. And then the obvious question is, do you have an idea of a future work for this?
Yeah, so
like for yourself.
Yep. So we are working on extending it to a richer class of constraints. So we are thinking of integrating it into the Z3 solver, so that you could have propositional structure in your input. So, like, if you provide a input consisting of if x equal to y, then a equal to b, else, those kinds of propositional formula. So in that, the Z3 would do the work of breaking down the propositional formula and then asking our string solver for solution of string equations that it gives us. So that is currently under the works. And we also want to reason about the tool itself. So right now, most of the rules that we use are formalized because they're written in ACL2S. However, the outer loop of the transition system is not formalized because the process of calling an external LIA solver is we just assume that it's a decision procedure, but we can't make ACL2S accept that it's a decision procedure. So
Cool.
there are ways around it. Like if for an unsat solution, you could think of generating a proof of unsat, and other such ideas are there.
Cool, thank you.
Ankit, one of your benchmark sets, I think, had the word fuzz in it, which leads me to believe that maybe there's some connection to fuzzing. Yeah, right here, string fuzz. Is there a connection to fuzzing? And if so, what is it?
It's a tool developed to generate string equations using fuzzing. So it's a master thesis by.
So they take a fuzzing approach to this problem.
Yep.
Okay, but does solving this problem give you any special power in a fuzzing context? Like, is there some scenario in which a security analyst has some set of partial equations and they need to fill in the remaining things to like crack the password or something?
Yeah, I mean, as I showed in the first slide, string solvers have become very relevant in all of these areas like string solving and verification and all of these.
Okay. Yeah, I'd be curious to know what somebody like Prashant, who does sort of language theoretic security, thinks of this. We should have one of those LangSec folks on in the future to discuss, because that connection seems interesting. Like intuitively, it seems like there should be a strong connection, right? But I don't personally know enough to know what exactly it would be.
Yeah, I have a hidden slide here. So
there you go. That answers my question.
Yeah.
Okay, cool. Yeah, there's a famous, I don't know if it's real, but there's a famous meme online that's a picture of a license plate that says drop asterisks on it.
Yeah, so today we have visual systems that can take pics of number plates and feed it into their system. So if you have something like this, that would be good.
So the second line is obviously bad, but the first one.
So in the second line, you have a variable x, and you just want to equate this string consisting of the variable x to whatever you get from this, to the value of input. And if it is satisfiable, then there's a problem.
Interesting. Okay.
In other words, is there a way to do an injection attack that will cause all the users to be dropped from the table? That's essentially what the query says.
Yeah.
Yeah, that's clever.
Cool.
One more question. For the proof of correctness, how does it work? Do you show that every rule on its own is correct, and then compositionally the entire non-deterministic procedure is correct?
Yeah, so the proof of correctness works in this way. We show that given a configuration, applying any enabled rule to it produces another configuration, right? And we also show that if a parent node or a configuration is satisfiable, at least one of its children is satisfiable. So satisfiability is preserved, and hence, if you started with a satisfiable configuration, you will end up in a SAT node. And similarly, if you started with an unsat configuration, your derivation tree will have all the leaves as unsat.
Gotcha. Thank you.
Also, in the case of if you provided a linear constraint, then it might be the case that all of the leaf nodes are unsat, but one of them is unknown. So in that case, we'll return an unknown. So if there is no sat and one or more unknown, we'll return unknown. If there is no sat and all unsat, we'll return unsat. But if we found SAT, then we'll generate the solution.
Yep, makes sense. Thanks.
Cool. Any last questions? All right. Well, Ankit, thank you so much for joining us today. This was a blast.
Thanks for having me.
And we'll be putting the video and audio up online.
Cool.
We repeatedly get more people watching the video and listening to the audio than I anticipate, which is cool. And I hope that continues to increase. And we really appreciate your time.
Cool. Thank you.
All right.
Thank you,
Adios.
Ankit.
Thanks.
Bye, guys.